Sorry, Elliot, I was just walking up. Drum roll, somebody. Serverless egress, I know everyone saw the description of this. And I'm not going to do it justice, I'm going to let you do it. I'm just going to say, this is Elliot, all right? One of our members, one of our very own, and be gentle.
I'm excited there's going to be something happening in Portland. I drove down from Portland. So, great. I'm new to this group. Really impressed with what you all have put together so far. So I have a small consultancy. We've been working with a global bank for the last year. And we did some things that we thought were neat. And we're trying our best to take some of those stories and share them. It's awfully hard to convince certain types of companies to publish things open source or to let any of that stuff be available. So I got permission to talk about some of the stuff that we did and even sneak out a little bit of code. So I'm excited about that. So as you can imagine, banking's been around for a very long time. Some of the technology is very, very old. Whenever I go into a place and they're complaining about like legacy stuff, like congratulations, like that's the hallmark of success. Like when you have legacy tech, that means you survived long enough for it to get old. That's a good sign. But then it comes with its own set of challenges. One of the other things that happens a lot with banks is that they buy lots of other banks, and so you end up having very different pockets of the organization, both technology and people-wise. And so you end up with things being built 2 or 3 times, very different philosophies, and so you might have a group that's very excited about trying some new technology, and then they've got to interact with very different technology stacks and groups that have a totally different risk appetite, different set of motivations. And so that's one of the harder things about doing change there. Introducing new techniques is that there can be a lot of skepticism, and each new set of people that you talk to, even though they have the same name on their business cards, can have a totally different set of experiences there and a different set of trade-offs and problems that have happened in the past that they're trying to avoid repeating. And so it can almost be harder to convince multiple organizations in a large bank to do something new than to convince multiple companies. So that's sort of the context, the scenario. So the goal that this little group that we were working with had was to build a proof of concept, but all the way to production, but a new set of financial APIs for open banking. And so part of the system, the core banking system, runs on a mainframe in Mexico. And then there's a set of people that run that and manage that. And then there was another set of APIs that were pretty clunky, APIs that had been developed a couple of years ago, all in Java, using more traditional techniques. I think they were running on some EC2 servers, definitely nowhere near serverless. And then this project was basically a translation layer. So what would it look like to stand up a more developer-friendly set of APIs for banking, connect them to the old stuff, and that involves like translating all the payloads so that the APIs that the developers see for hooking up to their mobile apps and things are just a lot friendlier and easier to use. And so there was enough, it was an isolated enough project that we got to try serverless and Bazel and some other technologies like that. And then one of the hardest parts was once we got all that put together and working, figuring out how to integrate with some of the existing control schemes. As a financial API that was new, relatively low frequency traffic. So, of course the goal was for it to handle things a lot more quickly, but as people were tipping a toe in the water and a new application would come online, it would start making a few test requests. But every single one of those HTTP requests was super important. When an important customer says, I want to try moving $100,000 from this account to that account, and they get a timeout, that's just terrible. They're not going to trust it to try it a second and third time. So we were particularly sensitive to some of the cold start problems. And then as we started going through the review with the risk groups and the security groups, they had existing control schemes around IP whitelisting. And it was important to them that we could plug into those existing control schemes. So like I said, rather than trying to change everything at once, convince everybody, lots of people had the power to say no. We decided to try and, separate from whether or not an IP whitelist is a good idea, we decided to try and make it work. So we could build some trust with those groups. Once we had that working, then we figured it would be easier to try and renegotiate some of those controls independently of whether or not this project was integrated. I don't think the IP whitelist is a very effective control, but that was the thing we were trying to make work. So we had set the goal for ourselves of not using any EC2 servers. We absolutely hate toil in the maintenance work that people have to do, and having to deal with patching and all of that stuff with the servers. Also having to come up with policy for when people are allowed to log into the servers, what they're allowed to do, making sure everything's clean. We've done it before on other accounts, but we just thought it would be great if we could avoid all of that. Because the goal we had wasn't necessarily like Lambda functions, the goal was reducing all of the toil associated with server maintenance. We were sort of okay with ECS services if they were running on Fargate. We were trying to get it working without any of those either, and just do pure Lambda, but as it turned out, Fargate was an escape hatch that was really important for us. We're particularly sensitive to cold start times. I mentioned that. And then we actually needed IP-based whitelisting both at the ingress and at the egress. Remember, we're like inserting ourselves into the stack here and doing a translation. And so we also need to demonstrate the capability of restricting inputs. And of course, that was kind of what our gut was telling us. We did actually measure with X-ray. Cold start times are actually way worse than I thought they would be. And we did a bunch of work to set up heartbeats. So the sort of standard thing that you do if you're worried about cold starts is you periodically make requests, and that heartbeat will maybe be slow. But any other request that comes along will hit an already warmed up function. There's a great analysis that was published about a year ago from Jan, which demonstrated that any request that you have in parallel, every single one of those parallel requests pays the cold start penalty. So we were still a little bit vulnerable to this, even though we were heartbeating every 30 seconds. We still knew, like, if a burst of traffic arrived, we were still going to get a big chunk of those requests that hit the cold start penalty. And we were seeing that happen in X-ray. Around 10% of the requests at different parts of the day. Either it'd be the afternoon, somebody would try some things, and about 10% of those requests would be way too slow outside of our service level objective.
When you say cold start, how many milliseconds are you talking or nanoseconds?
So I don't remember exactly what the original cold start was, but the important detail we ran into, we were already worried about cold start, and then we started looking into, we want to make the traffic from the serverless functions, from the Lambda functions, all come from the same set of IP addresses. And when we started looking at putting the Lambdas into a VPC so that we could control the egress IP, it was an extra 10 seconds. So it was less than a second, I want to say, for the original cold start, but then adding 10 seconds on top of that was just totally unacceptable. And that delay that's currently the amount of time it takes to provision an elastic network interface and attach it. And so that was just a non-starter for us. For some other context in the bank, the VP of engineering who was sponsoring the project had tackled a similar problem in AWS with EC2 servers a couple of years ago, and expected that it was probably a 2-month project. As it turns out, we were able to turn around in about 2 weeks, and that felt really, really good. And it's been remarkably stable since we did this. This was about 6 months ago.
Question, okay?
Yeah.
You said in about 10% you still saw that delay even with a heartbeat, or like keep alive or whatever. What is your goal? 100% or 99%?
I think the objective we had was 95%, and then we were going to try and drive that higher.
Okay.
And we weren't even putting any real traffic through it yet, so we just knew it wasn't anywhere near where it needed to be.
And okay. Or and which year was that? Or how long
That was
ago?
during the summer 2018.
Okay.
The cold start, are you talking about just specifically starting the service, or are you also considering scaling up out effectively?
Yeah, and so it absolutely, you incur that penalty scaling up as well. So like.
Was that also part of the problem you were trying to solve in this case? Okay.
Yeah, absolutely.
Mhm.
Because if you get a burst of 100 requests that come in at the same time, you now have to you have to boot 100 backends. And so any bursts that come through, even if you already had a handful of warm functions, you're going to pay that penalty on all of those ones that get invoked in parallel. So some extra constraints that we discovered as we started trying to hook this stuff up. API Gateway didn't support IP-based whitelisting for Ingress. And API Gateway has two modes. One is edge optimized, where it provisions a CloudFront distribution for you. And then the other mode is regional, where you can you get an endpoint that is specific to an AWS region. And the edge optimized API Gateway, which was running there, didn't provide enough customization. There's a little bit of customization, but not nearly enough of the underlying CloudFront distribution. Specifically, what we wanted to do was connect the AWS Web Application Firewall. And what hooking Web Application Firewall does is gives you IP-based whitelisting, in addition to a whole other set of handy controls that we thought they would ask for in the future: SQL injection, prevention, and some other useful things like that. It also introducing those rules introduced a different set of bugs, because as soon as we hooked up the whitelisting, then client calls started being rejected, and people weren't keeping track of the whitelist. Like, it's debatable whether it's a good idea at all, but this was the technical thing that we were trying to solve. So for Ingress, what we ended up doing was switching to regional API gateways with a custom CloudFront distribution that we set up. So that let us connect Web Application Firewall to CloudFront distribution. And we actually have development, production, test accounts. That CloudFront distribution connects to a regional API gateway. The regional API gateway is then fronting just totally normal Lambda functions, which we were trying to keep warm with heartbeats. The heartbeats themselves were Lambda functions driven by the AWS CloudWatch events scheduler. So you can set up a cron schedule in there, and that drives the heartbeating. And that all worked. So the tricky part was figuring out the custom CloudFront distribution. Once we got all that connected, that was no problem. Egress was a little bit trickier. We did not want to move the Lambda functions into a custom VPC because of that additional cold start penalty for attaching the ENI to every single backend resource that's actually running the Lambda function. So this is a picture just off of the AWS docs of how you get stable egress IPs. So you have a VPC. We did not have any web servers. We did not have any database servers. We did have the rest of the pieces. So you have your public subnet and private subnet. You have a NAT gateway, and then you can attach an elastic IP to the NAT gateway. Then any traffic that shows up inside here goes out through the NAT gateway, and it appears to come from that elastic IP, giving you your stable egress IP. Those are per availability zone. So for high availability, then we did 3 of them. And then the next part was getting traffic into the VPC so that it could come out through the well-known address. So we decided to create a custom proxy using Envoy. It was a little bit of a lucky guess picking Envoy. Other options you might choose would be like HA Proxy or Nginx. As it turns out, Envoy has been adopted by a bunch of other projects recently, and so that turned out to be a good choice. We thought it would be particularly good because Envoy, it was originally written at Lyft, but it's designed to operate as a sidecar service, and it's specifically designed to be cluster aware. and has some Lua extensibility, which turned out to be really, really handy. We knew we wanted to run this thing in a container and keep it really lightweight. So what we did was we defined an ECS service that was spread across those 3 availability zones, and gave it a little tiny container running Envoy. ECS takes care of running the service inside each of the 3 availability zones, and if we update the container, it takes care of bringing those down, bringing the new one back up. If one of them crashes or we restart it, it takes care of running it again. Because we defined that ECS service to be running on Fargate rather than on EC2, we can't log into the servers behind it. We don't have to worry about kernel patching and all of that stuff. And then we defined a load balancer that accepts inbound traffic and distributes it across all 3 of those availability zones, right? So you connect the load balancer to the ECS service, and it fans out for you. The load balancer also gives you health checking, and so if your service running there exposes a health check endpoint, when it goes down, say it's being replaced, you can immediately route requests around it. So, how do we actually make that proxy work? In the Lambda functions, we knew we needed to authenticate the traffic going through this proxy. We could not just leave it open. So the Lambda functions, when they boot, read from the EC2 Systems Manager parameter store. And so they retrieve an authentication token, and they're adding it into a custom HTTP header. So they're taking a request, mutating the body of the request to transform it to the legacy form, and adding an additional authentication token. There's already the original authentication token that's being passed through. And then we configure them to send traffic to the proxy instead of the real backend service. In the proxy, we also read from the parameter store and authenticate those incoming requests and just send them right on to the original backend service. Because the ECS service is running inside that VPC and it is long running, it doesn't have to restart all the time, that gets the traffic into the VPC and back out on the known IP address. And this is the entire configuration for Envoy is maybe twice as much YAML configured. This is a little hard to read. It's small, but this just shows you how simple it was to configure Envoy. This is actually inline code right here for an HTTP filter, and just this handful of lines is what's doing the authentication. So we've got a couple of things here, a secret placeholder and a previous secret placeholder. We wrote a little tool in Go that when the service boots up, it reads those secrets from the parameter store and injects them into the config file, and then starts Envoy with the real secrets in here. And then if an HTTP request comes in, if it's a health check, we just health check, we're okay. If it's not a health check, we check the custom header for text proxy auth and check whether it matches our current secret or our previous secret. That lets us do more frequent, do key rotation or password rotation with less downtime. Throw away the custom authentication token and forward on the request to the real backend service. Or actually, this is rejecting. If it falls through, it gets forwarded on. And that was it. That was the entire config for Envoy. I will have these slides available for you, so you don't have to worry about trying to read that code.
Cold start.
Yeah, cold start. So a couple of notes, things that were super helpful in this. One of the first things we did in that proxy was hook it up to proxy to HTTP bin. We're playing with request bin as well. That was super helpful with getting the config right. Like, are we doing the right thing, the thing we think we're doing as we're learning this new config language? Are we removing the headers we think we're removing? You know, what are all of the parameters that are being sent over to that backend service? Is it working the way we expect? We originally came up with something much more complicated until someone realized we could use a custom request header. Because we had an existing authentication token already in a header on the inbound request, we were originally doing a bunch of stuff with swapping tokens in and out and trying to store authentication tokens. This turned out to be much, much simpler. So the request coming into the proxy has the real authentication token and the proxy authentication token. We validate the proxy token and send the real token on to the real backend service. And there's an extra few hops in there, but it didn't show up in our measurements, and that was just such a better result than adding 10 seconds to every cold start. The whole thing together took about 2 weeks end to end, I think, to get up and running, and has been amazingly stable. We haven't had to touch it in a few months. Deployment of the proxies, deployment of both the ECS service and the Lambda functions is really, really simple. It's code pipeline doing CloudFormation stack updates. So even though those are totally different backend technologies, they're able to be driven through CloudFormation exactly the same way, which was really nice.
Did you use any templates?
Any what?
Templates for CloudFormation or just?
Yeah, so CloudFormation templates we've got a set, sort of a handful of microservices defined. And a bunch of those have serverless backends. And then we defined this, we call this our Egress microservice. And I hope another talk we can do sometime, it will be about the template processing language that we created on top of it. Funnily enough, after working on it for a year, I'm drawing a blank on the name, but Amazon came out with its own sort of way of extending CloudFormation templates.
SAM?
No, we were using SAM, but then they came out with something even more. It's written in Node.js, and it's like this thing that compiles and emits a CloudFormation template. It's like a whole processing layer on top of it. That's super handy. You're like, why would you want that extra layer? That sort of thing is super handy when you have things like 54 different Lambda functions, and you want all of them to get the exact same set of extra config wired up. So like, we want this exact same X-ray config on all 54 places. Like, rather than having to repeat it in all 54 templates, to be able to like put that at the top layer and say like, go decorate all of the serverless functions with this extra config. We did exactly the same thing for setting up log subscriptions and log retention periods. So there are certain attributes on those lower level things that you really just want to define one way for your whole environment and have it pushed across all of them.
Thank you.
We felt really happy to see recently at reInvent that Envoy was picked to power AWS App Mesh. And so that felt like it reinforced it as a good technology choice rather than HA proxy or Nginx for that proxy. We started looking at App Mesh to see like, could we throw away this whole thing that we built and just like configure App Mesh somehow? We haven't quite figured out how to do that, but it seems promising. I wouldn't be surprised if we figure out a way to actually remove the whole proxy service and just use App Mesh. App Mesh is designed around routing for and proxying traffic inside your cluster rather than like through your cluster. So it's not quite a perfect fit, but I wouldn't be surprised if it's possible. Another thing that kind of threw a wrench in the works for us was CloudFormation API Gateway domain name did not expose what the regional domain name attribute was. So we're building all of this stuff in CloudFormation. We provision that part, and we're going to connect CloudFront to it, and we can't get the domain name out of it. This happens again and again with CloudFormation, and I don't know if you all have had a chance to work with CloudFormation custom resources, but they're just fantastic as an escape hatch to work around some of that stuff. Even for connecting CloudFormation lifecycles to third-party APIs. So we created a custom CloudFormation resource. So what that looks like is you provision your API gateway domain name, and then you provision your custom resource and hand it the ID for that object. And inside there, the custom resource is connected to a Lambda, and it gets notified for all of the events in the CloudFormation lifecycle. So it gets notified like create, and then you can read attributes back out of it. So when that thing gets created, we would go use the raw API to look up the couple of attributes that we needed and expose them as attributes on a custom CloudFormation resource. That let everything connect through. About 3 or 4 months later, Amazon released an update to CloudFormation, and those attributes became available. So that's pretty common that some things might get left out because nobody needed them, and then you write custom resources, and over time, hopefully, you wouldn't expect to throw those things away. Probably less with third-party stuff. You end up keeping those for a long time. And I mentioned we made a little wrapper utility in Go.
I mean,
50 lines
lambdas
of code.
mainly in Go, or in which language do you use the lambdas?
What's that?
The lambdas you are using are mainly in Go, or what language are you using?
So I think we are using Java, Node.js, Python, and Go. And that sounds terrible, right? But that's also kind of one of the strengths of serverless. So the bulk of the team that's implementing all of the APIs with this handful of microservices is working in Java. That's what they're familiar with. They have a bunch of financial libraries available to them, and that was the right fit for them. Also, why we were particularly susceptible to cold start. The Node.js and Go and Python Lambda functions did not have as much of a cold start penalty. Then we were doing all of this glue, and we were hooking up some things in Cognito and some custom resources where they were already written in Python. So we were able to pick up those open source things and plug them in and make use of them. We're not going to rewrite them in Java just to make it the same language. The same
So what
thing.
kind of application was this?
This was a financial API.
Okay.
So moving money, issuing cards, checking balances, things like that. Creating accounts, creating cards. And then the utility stuff that we wrote, we're sort of a small sub-team. We enjoyed working in Go, and it was just really easy to write that stuff in Go. That was what we were familiar with. Each one of those little things is sort of fit for purpose. We had no desire to go try and force things into a different language when they really weren't on the same maintenance lifecycle.
Did you use AWS step functions?
We did not. We haven't had so far any reason to use step functions. They seem really interesting. We've been sort of looking at step functions around wiring up the deploys, particularly driving the deployment pipeline from development, security testing, sort of like sandbox or staging, and then out to production, and trying to hook up some logic there. I get super nervous about that stuff being too fancy. And so it seems cool, it seems like we can do some cool things, but we sort of haven't had the need hasn't been burning enough to take on that complexity yet. Yeah.
Do you have a diagram how these services and components were connected to each other?
So I didn't draw a picture, but this is most of the hops. So the web application firewall, going to CloudFront, going to regional API gateway, and going to Lambda functions. The Lambda functions are then calling a load balancer, which exists in the private VPC.
The load balancer, and from there to the Envoy proxy,
Mm-hmm.
then the proxy to those legacy backend services.
That's right. So it's taking a minute for the screen to update. So the Envoy services are running inside VPC, and they're just calling out to the regular backend services. Because they exist in the VPC with the way the routing is set up, they're going to be, their traffic gets pushed over to the NAT gateway. The NAT gateway replaces the source address with the elastic IP, and magically all the traffic comes from those authorized IP addresses.
And you needed that elastic IP at the NAT gateway for the whitelisting
On the
backend services.
Yep. So then we can say, here's our 3 IPs, all of our traffic is going to come from here.
Yeah. And And the envoy proxy is in a public subnet, so that the Lambda functions don't have to be.
The envoy proxy is actually in the private subnet, and then the load balancer is exposed publicly.
Okay. And because of that, you don't have to add the Lambda functions into the public subnet.
Exactly.
Yeah. Okay.
Exactly. And because the elastic load balancer is exposed publicly, we put authentication on it.
Okay.
There's a question here.
Yes. So, I mean, it sounds like, you wanted to write it in Lambda first, and then you realized, oh, we have to make sure we go from a specific IP, so you ended up adding, Fargate and
Absolutely.
handle it that way. Now, the question was, my question is, let's say you knew that was the requirement from the get-go.
Mhm.
Would you still write it in Lambda, or would you run some kind of API gateway in the Fargate? Because, I mean, you already have this infrastructure that runs containers that can run microservices. Would you just run everything there and not use Lambdas whatsoever?
That's a great question. Would we just run the API gateway directly in the VPC? I don't think that would let us, with the current limitations in AWS, I don't think that would have avoided the cold start penalty for
No,
us.
I'm saying run your own API gateway on the container service, right? Just don't use AWS at all. You already have your Kubernetes effectively, right? You can take in the traffic and run your everything on, basically.
I think that would be interesting. I think we would have needed to run our own serverless engine as well, like our own Lambda engine.
But that's what Fargate is, right? I mean, yeah, you can, I guess in that aspect, you could argue that you would need to make sure your containers that are providing the service need to be updated. But on that aspect, you probably need to patch your code too from time to time.
Sure.
So
I'd say if it was a team that was comfortable with running Kubernetes, I would have definitely been interested in running one of the Kubernetes serverless function services. They're all pretty raw. They're all pretty early. But if what we had was a team who was super comfortable with Kubernetes, that would have been a really interesting thing to explore. Absolutely. I think this problem is going to go away over the next year or two. It felt really good that even though we discovered the problem, sort of late in the game, that there was sort of sufficient building blocks available in AWS to get around it. I have one more set of. Oh, it's not updating. So we were trying to minimize the patching. One more. I totally left out a slide. Amazon released Firecracker. So when you look at what's happening there with like how quickly the instances are booting, I'm not sure where the code that implements an elastic network interface actually runs, but I can't believe that that's still going to take 10 seconds to boot in 12 months and 18 months. Like, I'm totally convinced that there will be changes in the software-defined networking layer that will make that just happen as fast as you need it to. So much attention has been paid on performance in other areas of Lambda that the extra fancy networking stuff, I feel like it just hasn't been as popular of a use case, and it will catch up.
So what is the database you're using for the backend?
For this particular product, it is a very old, very expensive mainframe in Mexico. So the service that we were writing was a translation layer, and so it didn't have any persistence directly in it. We've started doing some spikes around DynamoDB for some extra services that we're adding that don't exist yet, where we do need persistence, and those are using DynamoDB.
Wow, that's a long hop.
It is, but that was where the bank is operating their ledger.
And what AWS region are you using?
We were running in 2 regions, so our initial work was done in Oregon, and that feels really good to use green power. And then we had sort of a pilot going in Singapore, just to sort of keep us honest with everything that we were coding, that we weren't coding region dependencies in, so that we could, if the business was ready, turn up services somewhere else. The main driver there is not really network latency, it's, what's the right word? Jurisdiction. And so when you're providing financial services under different government regimes, like you need to sometimes provide those services in that jurisdiction. Yeah.
So with the cold solving the cold start problem, and so if you're with a solution that you put together, if there was a burst of 10, 20, 50 requests, I assume you would still hit a cold start penalty, but
yes.
The one without VPC.
Yeah, so that's very astute. We did not actually completely remove our vulnerability to cold start. In order to like further drive down the likelihood or the probability that we would hit a cold start, we would have to heartbeat more frequently and basically just send floods of traffic, which is not impossible to do. What we were specifically trying to do was keep those cold starts from going like half a second to 11 seconds, because that would just completely blow our allowable response time. Any other questions? Thanks for listening to this. I know it's like a lot of moving parts there, but I felt pretty happy that we were able to make it all work, and was really surprised to take off-the-shelf parts and put it together in 2 weeks and then not have to touch it. It was a really good experience. The company got a lot more confidence in AWS after seeing this project.
No, really, it's not, is it, so are you working as a professional services engagement or
Yeah.
some kind of these guys? It's Kindly Ops, your company?
Yeah, oh yeah, so Kindly Ops is my company, and there's like 5 of us. We do governance, risk, and compliance consulting. So our background is mostly as engineers, and people hate dealing with all of that security and compliance stuff, and we try and make the 2 work together with the least amount of misery. So that's the obsession with removing toil and still meeting the controls and all of that stuff. Well, thank you.
All right, thanks very much.